17 people wait in front of an elevator that has room for only 5. Count the number of ways that the first group of people to take the elevator can be chosen. So how many ways to choose 5 people out of 17? I imagine you could get away with writing as little as the following. 17, choose 5. The number of ways of picking 5 people out of 17. What is this equal to? It's equal to 17 factorial divided by 17 minus 5 factorial and 5 factorial. Now, the better question is, why is this true? Why is this the calculation? Well, let's look at a smaller example just so you can all be more comfortable with why this actually works the way it works. So let's say, and here's the example I usually go to. So, example, how many ways of picking 3 people, whatever, not a spelling class, out of 5? Picking, choosing, same meaning there. So let's think about this. Let's say we have 5 people, and let's say their names are Adrian, Bob, Camilla, Daniel, and Edgar. For obvious reasons, their names start with A, B, C, D, and E. So let's say we want to pick 3 people. So you could pick first person A, then person B, then person C, for example. How many choices did I have for the first person? Well, I had 5 choices. And then after I picked the first person, there were 4 choices left for the second person. And then after I picked the second person, there were 3 people left to choose for the third person. This 5 times 4 times 3, I'm going to write as 5 factorial divided by 5 minus, no, not 5 minus, sorry, apologies. I'm going to write this as 5 factorial over, holy smokes, yeah, 2 factorial. That's why I want to write this. I want to write, sorry, I did want to write it that way. I just got my brain screwed up here. That is not the full answer, because that is the number of ways of permuting, not choosing 3 people out of 5. Because I could pick any 5 people for the first one, right? So I could have picked A, then B, then C, but I could have picked B, then A, then C. That's a different order I picked them in, but it still results in the same group of 3 people. Adrian, Bob, and Camilla. Or I could have picked B, then C, then A. Or B, nope, not B first. Or A, then C, then B. Or C, then A, then B. Or C, then B, then A. And all 6 of these different ways, different orders of picking the same 3 people are getting counted differently in this 5 times 4 times 3. I need to account for that. I need to divide by the number of ways I might reorder these same 3 people. Well, there are exactly 3 factorial, 3 times 2 times 1, ways of permuting these 3 people. Or any 3 people, really. I'm just focusing on these 3 because it's easier to look at them. I don't want to overcount by 6. Or a multiple of 6, I should really say, a factor of 6. Right? This 5 times 4 times 3, which is equal to 120, that's 6 times 6 times? Yeah, 6 times too many people. Too many. 5 times 3. Sorry, I'm just thinking about. Sorry, my brain is doing. 1 second. Let me think for a minute here. 5 times 3. That makes sense. I'm going to divide by that too. Okay, yeah, good. Right on. So, yeah. What we're going to do is we're going to take this 5 times 4 times 3, and we're actually going to divide it by 3 factorial. That's the number of combinations. So this up here, this would be the number of permutations of 3 people. Like maybe someone asked the question where you're like, we want, actually, I'll say that in a second. I'll get back to that in a second. But the answer we're looking for here is 5 times 4 times 3, the number of ways of permuting any three people out of 5, divided by 3 times 2 times 1, the number of ways you can permute any three people that you choose, which we would prefer to write as 5 factorial over 2 factorial times 3 factorial. Or 5 factorial over 5 minus 3 factorial times 3 factorial, or 5 choose 3. Oh, sorry, yep. Let me see if I can zoom out just a tiny bit here. Okay. Which happens to be equal to 10, in case you're curious. Yeah, I feel like I'm saying something weird there. No, that's right. For some reason my brain is doing something weird. Yeah, right. 5 factorial. I'm sorry. Okay. My brain did something weird a minute ago. 5 times 4 times 3, I said was 120. It's not, it's 60. If I say something stupid, you are welcome to call me out. Like I'm not perfect. I make mistakes. You all know this. I might make a mistake accidentally. I might sound very confident about it because that's the way I talk about math. But like, if you think I've made an error, just say something, because I was having a problem because I knew that the 60 was an overcount by a multiple of 6. But 120 divided by 6 wasn't giving me 10, and I was getting really confused. But 60 is an overcount by a factor of 6, and dividing 60 by 6, I do get 10, which is what this should be equal to. So there are 10 ways of choosing 3 different people out of 5. But the better way to write this is 5 choose 3. You don't want to do the work to say this is equal to that. Just like here, you shouldn't simplify this at all. Even though it's not terrible to do, that's not the point of the question. The point of the question is to be like, oh yeah, 17 choose 5. Right. So let me ask you a different question. Let's say these same 5 people, now Adrian, Bob, Camilla, Daniel, and Edgar are running a race. How many ways, I'm going to ask this in an annoying way, how many ways can we fill what's it called, the pedestal where people stand when they win? Which is a terrible way to ask a question because it's assuming knowledge that people might not actually have. It's assuming that you know that filling the pedestal means we care about who's first, second, and third. So the way a person should ask this question is to ask, how many ways can there be a first, second, and third? Now we do care about the order that we pick the first 3 people. Picking A, B, C is a different meaning than picking A, C, B, because you've got a different first, second, and third. So now we do want the number of permutations, not combinations, of 3 people out of a group of 5. And I don't know a good notation for this. That's not entirely true. I don't love the notations available to me here. I will just point out, it is going to be 5 factorial divided by 5 minus 3 factorial. I would never write it this way, though. I would write this one just as 5 times 4 times 3. There are 5 choices for who comes in first, and then 4 choices for who comes in second, and then 3 choices for who comes in third. End of story. I don't want to divide by 6, which is 3 factorial, because I don't want to get rid of the different orderings, because each ordering is a different placement on the pedestal. Just so you are all aware, I know you don't get to use a calculator for your test, right? But you should just be aware, because you might have to take stats later on, use some of them. There is actually a button for each of these things on most calculators. It usually looks something like NCR for the choose function, and NPR is the permutation function. So if you actually wanted to find the numerical value for NCR, you would press, like for 5 choose 3 on your calculator, you would type 5, then the NCR button, which you might have to search for, then you would type 3, bless you, and then equals. And that would give you 10. Or if you wanted the permutations, you would do 5, and then the NPR button, and then 3, and then equals, and you would get 5 times 4 times 3, which is 60, not 120. And if you're not sure about this later on, feel free to come ask me. I'm happy to show you where it is, how to find it, how to use it. It's not that hard to find. But again, not the point here because you don't get to use it on your test. Yeah. There are other ways to write this. Some people write this as NCR like this, the choose function. We'll write this like this, just so you have seen it. All right. But again, if you're trying to choose a number of things out of a number of things and we don't care about the order, choose function. If we do care about the order, like a mixtape or a playlist is an example often that's used, we do care about the order and we want permutations. So the order did not matter for the first problem, but it does matter for the second. Exactly right. 100%. Couldn't have said it better myself. Okay, let's look at the rest of the questions on this last page. Of which one am I looking at here? I don't know. Midterm 2, the actual midterm 2, not one of the practices. All right, so let's see here. You have just enough time to play 5 songs out of 11 from your favorite album. In how many ways can you make a playlist to play the 5 songs? Does order matter here? Yes, it does. Annoyingly, yes, it does. It's different if you listen to School's Out for Summer before you listen to some other song, right? The order you listen to the songs in is noticeably different if you listen to one before the other versus the other one before that one. I know it's maybe not the nicest distinction to make, but you should just get it into your head that we're going to assume that playlists of songs or other things, order matters. And if order matters, we don't want combinations, we want permutations. So I want to make a playlist of 5 songs out of 11. Again, the way I would personally prefer to write this is the number of ways, 11 choices for the first song, times 10 choices for the second song, times 9 choices for the third, times 8 choices for the fourth, times 7 choices for the fifth. That's my answer. If you prefer, and you might prefer, I don't prefer, you could also write this as 11 factorial divided by 6 factorial. Because I want everything from, right, 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But then I don't want all of the stuff under 7. You mean the 2 there names. So that's why you can write it this way instead. But I feel like it's more work to think about how to write it this way than just to write it that way. Your choice. You got questions, ask them. I don't know of a notation for permutations. No, other than the annoying notation I wrote on the previous page. Like you might, although I don't think this is recognized as a standard notation, you might write this as like P11.5 or 11P5, but I wouldn't. I don't think that. You might ask her if there's a standard notation for it. I don't think there is, which is too bad. The tall parentheses notation is specifically for the choose function, meaning order doesn't matter. You could, if you wanted to, also write this as 11 choose 5, which means order doesn't matter, and then multiply it by 5 factorial to reorder all 5 of the things we have picked. All 3 of these ways of writing it are equal to each other. You should focus on the one that is easiest for you to conceptualize, which for me is this first one. But for you might be this one, might be that one. It might be this. This one actually is not that bad, right? Because you're saying 11 choose 5. I want to choose 5 songs out of 11. But if I'm just choosing any 5, order doesn't matter. But I'm saying here order does matter. So then I'm going to multiply that by 5 factorial because I'm going to think of there are 5 factorial, 5 times 4 times 3 times 2 times 1 ways of reordering those 5 songs that I've picked. factorial doesn't have a meaning in the context of choosing versus permutation. Factorial is just a mathematical notation. When you hear 5 factorial, you should think, oh, I'm just being lazy. It's kind of like an exponential notation. I'm writing 2 to the 6th because I don't want to write 2 times 2 times 2 times 2 times 2 times 2. I'm lazy. No, I'm really what I'm saying is, so there were 11 songs. Let's call them annoyingly A, B, C, D, E, F, G, H, I, J, K. I'm going to pick 5 of them. How many ways can I pick 5 songs? Well, there are 11 choose 5 ways of picking or choosing any 5 songs. Great, I picked 5 songs, but I didn't specify the order. Because when you're just choosing 5 things or how many things, we're not talking about a specific order in mind. We're just saying we picked these 5, just like we picked 3 people out of 5 people. We don't care what order we pick them in, we just picked them. But now we're saying, oh, shoot, I actually do care about which order I play these songs in. So after I pick these 5 songs, which there are a lot of ways of picking 5 out of 11 songs, then I'm going to take those 5 songs and say, well, I'm going to think about how many different ways I could listen to them. I could listen to the song A, then B, then C, then D, then E. Or A, then B, then C, then E, then D. And it's going to go on for quite a while. I don't want to write all these out because there's 120 of them. But, right, there's a lot of ways I could order these 5 songs. So I have to multiply the 5 song, the choice of the 5 songs I made multiplied by 5 factorial, because there are 5 factorials of ordering those 5 songs or different 5 songs, right? For every way I could pick 5 songs, 11 choose 5 of them, I'm going to reorder those 5 songs 5 factorial different ways, 120 ways. That's what's happening here. So there's 11 ways of picking, 11 choose 5 ways of picking or choosing 5 songs. And then there are 5 factorial ways of ordering the 5 songs we picked. Reminds me. No. Oh, no, I do. Cool. I have a handout for you all. I meant to do it last time, but I forgot to. So if you're not here in person, this handout, I think I posted it on Canvas, but I'm not, but I will if I haven't. It's just a handout on some basic probability stuff, some biology facts, and then cards on the back. Not everybody needs to play with cards their entire life. If you're not super familiar with the deck of cards or what these hands are, they're all listed on the back. Which right. So what I'm saying is, for the first song, I've got 11 to pick from. How many choices do I have? 11. I've picked one song. Now for the second song, after I've already picked one song, how many choices do I have for the next song? And then for the third song, and then for the fourth, and then for the fifth, I have 7. So that's the way I'm imagining this. And let's see what we've got here. For combinations, the choose function, only the identities of the object matter. Yeah, I guess you could think about it that way. That seems like a reasonable way of saying it. Order doesn't matter. Okay. Let's look at this third question on this last page here. Let me try and keep things in order. I'm sorry, I'm all over the place here. Oh yeah, we should definitely do one like that as well. Okay. California vehicle license plates take the form of DLLLD, meaning digit, letter, 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 digit, digit, digit. Where the first D is any number except 0. and the L's are any letter of the alphabet. How many license plates are possible? So how many choices do we have for the first digit? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 0. So there are 9 choices for the first digit. How many choices are there for the first letter? How many choices for the second letter? How many, right? Because we're not saying you can't repeat letters. Someone could make this question different and say, you're not allowed to repeat letters. And then it'd be 26 times 25 times 24. But they didn't. So 26 times 26 times 26. How many digits do we have to choose from here? 10 times 10 times 10. So if we want to write this more compactly, you could write it as 9 times 26 cubed times 10 cubed, if you felt like it. That's the number of distinct California license plates. This is the multiplication. What's the word I'm looking for called? Why is it not on here? There is a word I'm actually looking for. Like the multiplication property, I think, of combinatorics, which is basically if you have so many ways you can do one thing and so many ways you can do another thing, and you want to know how many ways you can do like each of those things, you multiply the number of ways together. You take a survey with 5 yes or no questions. How many different ways could you complete the survey? All right, 5 questions. How many choices or different answers could you make for the first question? 2. How about the second question? How about the third question? How about the fourth question? 2 times 2 times 2 times 2 times 2, which I would prefer to write as 2 to the 5th. And I would leave my answer like that. None of these answers, in my opinion, require you to actually find the exact number. Oh, did you want to see the thing then, maybe? Oh, sorry. Okay. Right. You just have to find the correct expression for the thing you're trying to find. Yes, 2 to the 5th is 32. You could certainly write that. It's totally fine to write that, but that shouldn't be the main focus of these problems. Okay. Should we look at the different practice tests for some other problems like this? Okay, let's take a look, see if anything's particularly different here. No, well, let's look at this one, sure. Let's look at practice midterm 2-2. Again, looking at problem 7. And I keep throwing stuff all over the place here. And then we'll see how we feel about more probability. How many 10-digit numbers? What is it? 5, I think. Yes. How many 10-digit numbers can be formed using a 3 and 7 only? Kind of a weird question. But I think I know what the answer is, or how to think of the answer. How many choices? So there's 10 digits, right? How many choices do you have for the first digit? How many choices for the second digit? And every digit, there are 2 choices, either a 3 or a 7. So our answer here is 2 to what power? Right. That's it. In how many orders can a deck of 52 cards be shuffled? Well, every card is different, right? So any different way of ordering them is going to be counted as different. So there's 52 choices for the first card, 51 choices for the second card. So the number of ways to shuffle a deck, or the number of ways the cards that can be shuffled is probably the more appropriate language here, is a very common 52 factorial. This is a very common number that comes up in probability because we talk about shuffling cards in the deck. That's it. So most of these problems are not numerically challenging to calculate. It's just wrapping your head around like what I'm actually trying to think about here. A girl has invited 5 friends to a dinner party. After locating herself at the table, how many different seating arrangements are there? So we've got 6 seats at the dinner table, and the host has sat herself right there. And then there are 1, 2, 3, 4, 5 seats left. I will say for these problems where you have someone sitting around a table, you almost always have to first place one person. Otherwise, you could have sat, right? You could have sat them there and then had the same sort of arrangement by just rotating things around. So typically for these around the table problems, you have to sit one person down. There's probably, you don't, and there's really not a different number of ways of doing that. That's just like a thing you do. And then after that, you ask yourself, okay, how many ways can I arrange the rest of the people? Well, different people are different. So there are 5 different choices for who sits on the left side of the host. And then there are 4 choices left for who sits here, and 3 choices left for who sits here, and 2 choices left, and 1 choice left. So the number of ways we can see our 5 guests after we have sat down is 5 factorial. Interesting that none of these problems have any choose. Oh, the last one does. I'm like, there's no choose questions yet. That seems surprising to me. Question 8. How many committees consisting of 3 representatives and 5 senators can be selected from a group of 5 representatives and 8 senators? So we have 5 representatives and 8 senators, and we want 3 representatives and 5 senators. And it's annoying. I would have picked a different number than 5 there. Oh well. Seems like it can be confusing that there's a 5 there and there. Whatever. Okay, so if you've got 5 people, how many ways can you choose 3 of them? We said all the words already. 5, choose 3. So the number of ways of getting the 3 representatives out of 5 representatives is 5, choose 3. We could actually list them if you really wanted to, just so you can see it. I'm happy to do that if you want to see it, but we don't have to do it. There are 10 ways. 5, choose 3 is 10. And then how many ways of getting 5 senators from a group of 8 senators? Well, 8, choose 5. I will point out, just because it could come up, although I don't think it really will, 5, choose 3 is the same as 5, choose 2. And 8, choose 5 is the same as 8, choose 3. Because the number of ways of picking the people that are in the group is the same as the number of ways of picking the 2 people that aren't in the group, or the 3 people that aren't in the group. So you can always think about picking the things that you want to include or the things that you want to exclude. And the number of ways of picking the included things versus the excluded things is the same. An easier way to think about this is how many ways can I pick 4 fingers out of 5? Well, instead of how many ways can I pick 4 out of 5, how many ways can I exclude 1? Well, 1, 2, 3, 4, 5 ways of picking the one I'm going to exclude. Or 1, 2, 3, 4, 5 ways of picking the 4 I'm going to keep. Same thing. I thought I saw a hand or a question over here. Yeah, Jocelyn. 5, choose 3 is 10 because that's how it ends up calculating. So the whole answer here is a 10. I was just pointing out that we see 5, choose 3 often enough to know that 5, choose 3 is 5 factorial over 5 minus 3 factorial times 3 factorial. When I write this, I'm really thinking of this as, I'm going to write it out, 5 times 4 times 3 times 2 times 1. 5 minus 3 is 2. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. The 3 2 1s cancel, and we're left with 20 divided by 2, which is 10. But again, we don't probably really actually need to know that. I was just kind of flippantly saying, yeah, 5 choose 3 is 10. Because I could pick, so let's say I pick U3 as the representative, right? And then from the 8 senators, I'm going to pick 5 of them. But no matter which 5 I pick, they could go with U3. And there's 8 choose 5 ways of picking, which is a lot, right? It's like 8 times 7 times 6 divided by, it's like 56 ways of picking those other 5 people. So for all 56 ways of picking those 5 senators, I can group them with U3 representatives. But then I can also group them with U3 representatives. or U3 representatives, or U3, or U3. So all 56 of those pair of groupings of the senators has to get matched with each grouping of representatives, which is why we multiply them together. Oh, sorry, I forgot there. Okay. Yeah. Let me take a quick gander at the rest of these probability questions and see if there's anything that looks noticeably different. This one does look kind of hard. Sure, let's look at this one, and then we'll probably leave the last one, but we'll see. Because there are a couple other things we should address before we're done today. So I'm going to take a look at the probability questions from practice midterm 2-3. How many, I think this question might be more interesting. How many 4-digit numbers can be formed from 1, 3, 5, 7, and 8 if none of these numbers appear more than once? Okay. So does order matter here? Yeah, order matters, right? 8, 1, 5, 7 is different than 8, 1, 7, 5. So in our 4-digit number, I will say something we don't really talk about here, but a very common tactic for doing any of these problems is writing out the spaces for the things you are picking. That is almost always what I first do if it makes sense to do it. How many choices do I have for the first digit of this number? 5 choices. How many for the second? They can't repeat them, so I only have 4 choices. How many for the third? And then 2. Which again is the number of ways of permuting 4 things out of 5 things. I would leave it like this and just say it's 5 times 4 times 3 times 2. It technically would not be incorrect to say 5 factorial, because 5 factorial is just 5 times 4 times 3 times 2 times 1. Even though I think it doesn't have the right meaning, it is still the numerically correct answer. If I was writing this out in a different way, I might write it as 5 factorial divided by 1 factorial, which seems extra annoying. Yeah, that's all I want to say about that. Well, because what is 5 factorial? But I really don't want the 1, so I'm dividing by 1 factorial, which is just 1. But it's the convention, right? If instead it was how many ways could I make, say, like a 3-digit number, right? A 3-digit number with the same digits, it would be 5 times 4 times 3, which I would write as 5 factorial over 2 factorial, because I'm missing the 2 times 1. What if I could repeat digits? Sorry, what was that? Right, exactly. It would be 5 times 5 times 5 times 5, which is 5 to the 4th. All right, let's see what else is on this page. A certain college has only 3 unit courses and 13 of which freshmen may enroll. Okay. Find the number of 15-unit programs. Okay, so this is just the same question you had before, made more difficult by making you do a little bit of math before you get to the point. So we want to enroll in 15 units, and there are 13 3-unit courses to choose from. So of those 15 units, how many courses do we have to pick to meet that? Right, we need to pick 5 courses out of how many? 13. That's the point, is we're doing 5, we're thinking about how to choose 5 out of 13, because the order we register for your classes in, I mean, assuming that everything is fine and easy and you get to register and there's no wait list, whatever. It doesn't matter if you register for biology first and chemistry second, or chemistry first and biology second, right? Because we're not saying that we have like different times or whatever. We're just saying you're registering for the courses. So we want to choose 5 courses from these 13, I'm assuming unique courses. Although it doesn't really matter, I guess. So the answer is, of course, going to be 13, choose 5. That's it. But then, oof, okay. So then there are, I think it's funny. Okay, yeah. Then the second part of this question is the requirements. The requirements are Math 17A, which is not a 3-unit course at UC Davis, and Biosci 2A, also not a 3-unit course at UC Davis, are required. But we'll pretend like they're 3-unit courses because I'm sure that was the intent. If you run into something like that where you're not sure, you can always ask. But the intent here, I think, makes it relatively obvious that, yeah, those are courses we have to pick. So if those are 2 courses we have to pick, how many courses are left that we still need to choose? Not how many, not how many are there left to choose from? How many do we still need to register for? 3 out of how many there are left to pick from? 11. So now that we have these 2 already chosen for us, there are 11 choose 3 ways of picking the rest of the 3 courses out of the rest of 11 courses, right? There are 11 courses left to choose from. And there are 3 courses left to choose. So that we have a total of 5 courses. Okay. All right. Question C looks interesting here. I'm sorry, that was like number 10 or something. Try to number things. In how many seating arrangements can 8 men be placed in a row of chairs? All right, I heard 8 men in a row of chairs. I'm drawing 1, 2, 3, 4, 5, 6, 7, 8 spaces. That might not actually be the right thing to do here, but I'm going to do it anyway because it's just by habit. If there are 3 who insist on sitting together, okay, right? Consider 2. Oh, they even give you a hint. Consider 2 seating arrangements different. Oh, it's not a hint. It's more instruction. Sorry, I thought it was a hint. I thought they're saying consider these 2 things. Consider, that's why it's good to read the whole thing before you start saying or thinking stuff. Consider 2 seating arrangements different unless each man sits in the same chair in the 2 arrangements. Oh, okay. I see what they're getting at. All right, sure. All right. So first of all, let's think about where we can seat these 3 men that have to sit together. Well, the 3 men could sit in the first 3 seats, or in the second 3 seats, or in the third 3, or in the fourth 3, or in the fifth 3, or in the sixth 3. There are 1, 2, 3, 4, 5, 6 groups of 3 chairs that those men could sit in. Or another way of saying it is, what is the leftmost chair that one of those 3 men has to sit in? Oh, it's chair 1, 2, 3, 4, 5, or 6. The leftmost man can't sit in chair 7, can't sit in chair 8 in this group of 3 men. Okay, so there are 6 choices for where the leftmost man in the group of 3 men sits. They should have made the other 5 people women. I feel like that would have made it easier to visualize this question. Why don't we do that anyway? Let's just imagine that the other 5 people are women, just to make it easier for ourselves. So the 3 men have to sit together. We're going to pick a seat for them. So there are 6 ways, 6 choices for where, I don't love that that's a 6, but it is. The leftmost man sits. I wish this had been out of 7 instead of out of 8, but oh well. I'll tell you why in a minute, because I just feel like it's going to make it a little bit more confusing. Fine. After we decide where the leftmost man sits, how many ways are there of arranging the 3 men in the 3 seats they're going to sit in? So let's say we picked these 3 seats for the 3 men to sit in. Mans A, B, and C. How many ways are there of ordering the 3 ways that the ways that those men sit? It's not 3. 3 factorial, 6, which is why the 6 here I felt like could be a little confusing because they're not at all related to each other. They just happen to be the same number. So yes, there are 3 factorial equal to 6 ways of seating those 3 men. Now that those men are sitting down in their 3 seats, how many ways can we arrange the other 5 people that also have to sit down? Other 5 women, as far as I'm concerned. That's like the nicer way to think of it. There's 5 women, 5 factorial, right? There are 5 ways, right? Because every different ordering is a different seating. Because if you sit in a different seat, it's considered a different arrangement. So there are 5 factorial, which is equal to 120 ways of seating the other 5 people. And we're going to multiply all these things together. We want 6 ways to place the leftmost man times 3 factorial ways of seating those 3 men in those 3 seats times 5 factorial ways of seating the other 5 people in the other 5 seats. So 6 times 3 factorial times 5 factorial. Which again, I would leave like that. This problem, I feel like it's easy to miss the first 6. That to me is the hardest thing to see how to get as far as like not having as much practice with this. Yeah, really like thinking about where the leftmost, or if you prefer the rightmost man can sit is the way we often do it. Yeah. All right, let's look at the last question on this practice test, and then we will do other things, and we can come back to probability if you all want to. Sure. So the first man, the leftmost man of the 3 men that are getting seated together could sit here. Could sit here, or here, or here, or here, or here, but can't sit here or here. Because if he's the leftmost man, there have to be 2 men to the right of him. Cool. All right. How many permutations of the letters of allele exist? Okay. So, how many letters are there? 6? 6, yeah. There are 6 letters. And let me just point out, if the letters were all different, like for example, if our word was a 6-letter word that didn't have any letters that repeated, which would be something like, I'm just gonna make a word that's not a word. ASTEND, astend, right? My favorite word. But if you had a word, people say word, when people say a word in math, they mean an arrangement of letters that might be a real word in English or another language or not, but they just mean an arrangement of letters. So here's a 6-letter word. And for this one, there are 6 factorial permutations. There are 6 factorial ways of reordering these and getting a different thing every time. There are 6 choices for the first spot, 5 for the second, 4, 3, 2, 1. Now here, there are also 6 factorial choices, except we have 3 different L's and 2 different E's. So the problem is when I rearrange these 6 letters, I might get something like this. Let's say I get L1, L2, E1, E2, L3. And at least in the beginning, I might count that differently than L1, L2, E2, E1, L3. I'm thinking of those as differently, even though I shouldn't be. I'm going to fix it. So at least at the beginning, I'm thinking, okay, there are 6 factorial ways of rearranging. If, it's a big if, we distinguish between E1 and E2 and L1, L2, and L3. Okay, but here's the point. We're not going to distinguish between those letters, right? You're not writing words and saying the first L in this word is L1 and the second L is L2. You're just writing some L's. Another question that people often ask that is they ask the same question for a word like Mississippi, which is a great one. So here, what we're going to do is say, well, there are 6 factorial ways of rearranging this, but then in all 6 factorial of those ways, we're double counting for the e's, right? Every word that shows up with an E1 and E2, it's going to show up with E1 and E2 in a spot, and then E1 and E2 in the same spot, but interchanged. So we have to take our 6 factorial and divide by the number of ways that you can rearrange the two e's. 2 factorial. That's the number of ways to interchange the e's with each other and not change the word. How many ways can we interchange the l's with each other? 3 factorial. And just for fun, just to make it kind of make sense, how many ways can we interchange the 1a with itself? 1 factorial. The reason I ask that is because if you do this for all the letters, the denominator, if you ignore the factorials, the numbers in the denominator should add up to the number in the numerator. And actually, this is like the multi-choose function. This is actually 6, choose 2, 3, 1. I don't actually know if that's the way you say it, but this is the thing. Just for fun, not just for fun, to illustrate the point, if you want to do it for Mississippi, which is MI, double SI, double SI, double PI, how many letters are there? I think there's 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nope, there's 11. 11 letters. So there's 11 factorial ways of rearranging them. How many ways of rearranging the 4 S's? How about the 4 I's? 4 factorial. There are 4 I's. How many ways of rearranging the 2 P's? And then the 1 M. 4 plus 4 plus 2 plus 1 is 11. So this will always work for this kind of question. If you want to know the number of different words you can get by rearranging the letters in your original word, it's just the number of letters factorial divided by the number of each letter factorial. So the number of S's factorial, the number of P's factorial, the number of whatever is factorial. You don't have to write the 1 factorials because that's just 1, but you could if you wanted to, and it wouldn't be wrong. Cool. All right, let's change what we're doing. Not that we couldn't talk about probability more, but just there are at least a couple things I wanted to address. One, because, so I did notice that at least on one of the practice exams, you did have to find the solution to a system with imaginary eigenvalues, which seems to random. But she does give you the general solution for imaginary eigenvalues on the front of the test. So let's do one of those just to remind ourselves of how it works, because it is kind of a giant pain, but it might be on your test. So giant pain or not, you might have to do it. So I think I have an example. Yeah, I'm pretty sure this example is what, yeah, I think so. So let's say our system looked like this. dx dt is equal to x plus y, and dy dt is equal to negative 8x plus 5y. And I forgot to give myself initial conditions. Now let's say our initial conditions or our initial value problem, we're told that x of 0 is equal to, I'm making something up, it might turn out to be terrible, and y of 0 is negative 6. Hopefully that won't be the worst thing ever, but it can't be that bad. All right, so we're going to start off by doing the usual thing. Find the matrix, find the eigenvalues, find the eigenvectors. So matrix is 1, 1, negative 8, 5. Eigenvalues. So determinant of A minus lambda I. Sorry, just as a reminder, especially if when you're classifying systems, or actually, see, mostly I think for the Jacobian problem, like where you have to find the partial derivatives and all that kind of jazz, it is almost a guarantee that most of your matrices, after you plug in your equilibria, you're going to have a 0 in the upper right-hand corner or the lower left-hand corner, except for maybe one of them, which means, sorry. Yeah, sorry, upper right or lower left, which means your matrix, the eigenvalues are just the diagonal elements, the upper left and the lower right-hand corner. So use that fact. You are welcome to use that fact. I can't imagine she expects you to do any work to find them other than to be like, there they are, beautiful and lovely. But that's not the case here. So we actually have to do the work. So it's going to be 1 minus lambda times 5 minus lambda minus -8 equal to 0. That's going to be lambda squared. Minus 5 lambda minus lambda is -6 lambda plus 5. Ooh, we're not moving around enough in here. Plus 8 equals 0. So lambda squared minus 6 lambda plus 13. I mean, I guess it's not like it's terribly dark in here, so it's fine. If you want to wave your arms around, you could like try to make the lights go on or not. So this definitely doesn't factor, right? I don't know how to multiply to 13 and have to -6. So definitely quadratic formula is what's required here. So our eigenvalues are going to be 6 plus or minus the square root of -6 squared minus 4 times 1 times 13 all over 2 times 1. So we're going to get 6 plus or minus the square root of, okay, 4 times 13 is something I do encourage you all to be good at because it comes up more often than you think. And it's just the number of cards in the deck. There are 4 suits in a deck. There are 13 ranks in each suit, and 4 times 13 is 52, the number of cards in the deck. Or twice the number of letters in the alphabet. So 36 minus 52 is definitely a negative number. So we get 6 plus or minus the square root of -16. What's the square root of -16? 4i. And I do think it's worthwhile to simplify your imaginary or complex roots as much as possible, just to make the rest of the problem easy to work with if it's the one where you have to do the whole finding the solution. All right, so there are eigenvalues. Lovely. Let's find the eigenvectors. So we're going to just focus on lambda equal to 3 plus 2i. We usually pick the one with the positive real or imaginary part just because, I don't know, that's what we do.
I have a question about I, like, what is, like, I squared equal to?
I is equal to the square root of -1. So really what we're doing right here with the square root of -16 is we're actually saying it's equal to the square root of 16 times the square root of -1. Square root of 16 is 4. Square root of -1 is I. And then I squared would be the square root of -1 squared, which is -1. Is it +6 or is it -6? I think it's +6, right? Because when you do the quadratic formula, it's -b plus or minus the square root. Also, another way to remind yourself is that my trace for A is my trace positive or negative? Right, my trace is positive, which means I know I have instability. And over here, oh yeah, my real part is positive. I have instability. Good, we're good. Okay, so now the eigenvectors, which is not my favorite part, but we're going to do it. So this is definitely where I do prefer doing it the way you've been doing it in class. So we're going to do 1 minus lambda. So 1 minus, you should make sure you get some parentheses around that. 3 plus 2i, 1, -8, and 5 minus 3 plus 2i times your unknown eigenvector equal to 0, 0. And just like every other time we've done this, or almost every time we've done this, you can choose either row you want. I would choose the row that had smaller integer numbers. I'm going to pick the first row here. I'm going to say that -2 minus 2i, because that's what this is equal to here. -2 minus 2i times x plus y, or 1 times y, equals 0. So y is going to equal +2 plus 2i times x. So doing the thing we always do, picking x equal to the coefficient of y and y equal to the coefficient of x, or just setting x equal to 1 and figuring out what y is equal to, my eigenvector is going to look like x is 1, y is 2 plus 2i. And then, not that we really even need this. I don't think you actually need this. No. Yeah, sure, we can say it anyway. So if lambda were equal to 3 minus 2i, then the eigenvector would be 1 and then 2 minus 2i. You literally are just changing all the imaginary parts to the opposite sign that they were. Okay. And then this is where I would have to go look at the formula because you should never memorize the terrible formula we're about to use. Questions before we move on to the next part then. Okay. So we've got our eigenvalues, we've got our eigenvectors. Let's write them down again on the next page just so we have them here. So our eigenvalues are lambda equal to 3 plus or minus 2i. Our eigenvectors are v equal to 1 and then 2 plus or minus 2i. Okay, so now we're going to use the formula. So here's what we do. We need to write first your eigenvectors as a vector of real things plus or minus the vector of imaginary things. So we're just going to break this up into the real part plus the imaginary part. So I'm going to write my vector v as, okay, the real part is 1, 2, plus or minus 0, 2i. I wrote the I in there because it was easier for me to break it apart that way, but the technically correct way of writing this would be 1, 2 plus or minus I times 0, 2. So 1, 2 is my U vector, 0, 2 is my W vector. And all I'm doing is following the format that was given to me. Also a reminder, in lambda equal to 3 plus or minus 2i, the 3 is your A, the 2 is your B. So A equals 3, B equals 2, U equals 1, 2, W equals 0, 2. Okay. So I broke up the vector V here into the real parts plus the imaginary parts. So what I really did was I thought of one way to kind of think about this is I'm thinking of V as 1 plus 0i in the first part and 2 plus or minus 2i in the second part. So the real parts right there, the 1 and the 2, the imaginary parts right there, the 0 and the 2i, or the 0 and 2 times i. Cool. And then that's A, that's B, so now what I'm going to do is I'm going to look back at the front page of my test. Like, okay, there's the gross formula I'm trying to plug everything into. So I'm really just going to write my solution now. And I might have to fix it in a minute, but at least I'm going to start off with the following. Okay, so A is 3, B is 2, U is that, W is that. So I'm going to get the solution here is equal to C1 e to the 3t times cosine of 2t times U minus sine of 2t times W, and you don't put the I in there, it's just 0, 2. Plus, I don't have enough room, so let's move down here. C2 e to the formula 3t times cosine of 2t times W, which is 0, 2, plus sine of 2t times V, which is 1, 2. Gross. Okay. You could compactify this if you felt like it, but I probably wouldn't. I would probably leave it as is, to be perfectly frank. So we still have one more thing to do. We still have to find C1 and C2. So what we're going to do is we're going to, remind ourselves that this X is really what X and Y are both equal to. And we're going to plug in our initial conditions. We're going to plug in T equal to 0. And what dumb things did I choose for X and Y? 4 and -6. X equal to 4, y equal to negative 6. Let's see what we get when we do this. So here's an important reminder, or here's an important question. What's sine of 0? You have to know this to do this part. It's 0. What's cosine of 0? Great. So when we do this, oh, what's e to the 0? Okay, cool. So I'm going to get well, actually, on the left hand here, I'm going to get 4 negative 6 equal to C1 times e to the 0, which is 1, times cosine of 0, which is 1, times 1, 2, minus sine of 0, which is 0, and I shouldn't even think about writing anything over here. I should just write nothing. Plus C2 times e to the 0, which is 1, times cosine of 0, which is 1, times 0, 2. Plus sine of 0, which is 0, and I shouldn't write anything over there either. Not that terrible to do this part, but you definitely have to remember to make your life easier by remembering that sine of 0 is 0 and cosine of 0 is 1. All right, so now writing this out a little bit more nicely, I've got C1 times 1, 2, plus C2 times 0, 2. Oh, and this is super nice when you have a 0 in one spot. You also be able to look at this without any effort. Show me on your fingers what C1 is equal to. I want to see some fingers. More than that many fingers. C1 should be more than 2. C1 should be 4. How do I know it's 4? How do you know it's 4? Because 4 times 1 plus whatever this is times 0 has to give me 4. So when you have a 0 in one of these spots, if I have a 0 next to C2, it's really easy to figure out what C1 is by focusing on the same row that has that 0 in it. So definitely C1 has to equal 4. And then we have in the bottom row, negative 6 equals 4 times 2 plus C2 times 2. So negative 14 equals 2C2. So C2 equals negative 7. And then to wrap this up, you should go back and write the whole thing over again with C1 and C2 plugged in. But if I was strapped for time, I might draw some little arrows and be like, that's going to be 4, and that's going to be negative 7. Or even, erasing seems like a bad idea. Yeah, so I should say, that is the solution to the system. The solution to this system of equations is 4e to the 3t times cosine of 2t times 1, 2 minus sine of 2t times 0, 2 plus negative 7e to the 3t times cosine of 2t times 0, 2 plus sine of 2t times 1, 2. It's gross, it's long, but that is the solution. Question?
At the end, we put like cosine 2t 1, 2 minus sine 2t 0, 2.
Like right here?
Yeah, like that part, and like the cosine 2t 0, 2, where like I think
Where is that coming from?
no, I get that, but like I was looking at the solutions.
Mm-hmm.
I think like the ones with the zeros, like cosine 2t 0 and sine 2t 0, like they're not in the solution. Is it? Like I was confused.
Well, so this is a problem I made up. So I'm not sure what solutions you're looking at.
Well, for this type of problem,
Uh-huh.
I feel like I'm not sure, but I think it's like that 0. Do they like put that like that? Do they do 0 times sine 2t?
Okay, so here's what so what I think you're saying. So let's say we wanted to write the solution and we wanted to write it as compactly as possible. So again, I'm advocating for not doing this because I think it takes up too much time. If it were me, I would leave my solution in the following way, but then I'll show you what I think you're getting at. So the solution is 4e to the 3t times cosine of 2t times 0, 2 plus sine of 2t times 1, 2 minus 7e to the 3t times cosine of 2t times 0, 2 plus sine of 2t times 1, 2. This is how I would leave my answer because it's technically correct and doesn't require any more work. But if we wanted to, we could make this a little bit more compact and say, well, what we really have here in this first parentheses is cosine times 0.
Is that supposed to be or 1, 2, and then 0, 2?
Oh, sorry, I did go. Yeah, sorry, sorry about that. I got those backwards. Thank you. I think my gaze slipped down the line accidentally. Yes, okay. So here we have in the first row cosine of 2t times 1 plus sine of 2t times 0. Let's not write that. And then in the second row, we have cosine of 2t times 2 plus 2 times sine of 2t. Probably don't need the parentheses and the brackets, but oh well. And then over here, same deal, minus 7 e to the 3t times cosine times 0 plus sine times 1. And then in the bottom row, cosine times 2 plus sine times 2. I feel like I missed a sign. Yeah, sorry. That should have also been a minus sign there. I apologize because, again, my gaze slipped a little bit there. That should be a minus like it was right there. Sorry about that. So that should actually be a minus sign there. And then we have over here 2 cosine plus 2 sine. Is that what you meant?
Yeah.
Cool. And then I say one sec. If you really wanted to, you can combine this into one vector and write it as 4 e to the 3t cosine of 2t minus 7 e to the 3t sine of 2t. And then the bottom, 4 times 2 is 8, minus 7 times 2 is negative 14. 8 minus 14 is negative 6 e to the 3t. And you can only do that because they have the same e to the whatever, cosine of 2t. And then 4 times negative 2 is negative 8. Minus 7 times 2 is negative 14. Minus 8 minus 14 is minus 22 e to the 3t sine of 2t. Notably, when you plug in 0 for t, you get 4 minus 0 and negative 6 minus 0. And that's the initial conditions for negative 6. Again, I would encourage you all to stop here unless you were specifically told you need to write it more compactly, because it's the same answer, just less work. Questions?
Yeah. So, can you go back to the old one? Okay, so my question is, say you what we just did, like this 0 times the sine and 0 times the cosine, right?
Mm-hmm.
Could you do that before you solve for C1 and C2? Because like it'll simplify.
I mean, you could, but I don't see the need to. Personally, I don't see the need to. I feel, I mean, yeah, you could totally, if you wanted to, get to here before having found the 4 and the negative 7 there and have like C1 e to the 3, 2 times this minus or plus C2 e to the 3, 2 times that, and then plug in t equals 0 and solve for C1 and C2 if you like. That would also be totally fine. And maybe easier to do that way. Okay. There was one other question I said I promised I would get to for someone, which so I would say hopefully the one you have to solve, because it sounds like there's going to be one you have to solve by finding the eigenvalues and the eigenvectors and then writing the solution using the initial conditions to find C1 and C2. Hopefully they'll be real numbers, but they might be imaginary. If they're imaginary, the formula is going to be on the front page of your test, or maybe on the page that the problem's on, and you will need to use this to write your solution. You'll have to identify A and B, right? A is the real part of your eigenvalue. B is the coefficient of the imaginary part, but still just a real number. And U is the real part of the vector. W is the imaginary part of the vector, but it's still a real vector itself times I. And then you just toss everything into this terrible gross formula, which you should never memorize ever. Don't even think about it. It's terrible. Question? Mm-hmm. Yeah, I mean, it's terrible, but yes. Normally, that is not what happens. Normally, the initial condition they give you is when t equals 0. But you're right. they could give you a different initial condition at a different time, and then finding C1 and C2 is a lot less nice. But yeah, in theory, yes, that is possible. In practice, I don't imagine that's what would be asked, but it could be. All right, so someone else had asked me about this thing about how problem 5 in the exam will be somewhat different from the problems in the practice exams. You'll be asked to sketch trajectories around equilibrium points. The problem will read like this: a system given explicitly, meaning you're given the differential equations, I assume that's what that means, has a saddle at -2, 5, has an unstable node at -1, 2, a stable spiral, yeah, at 1, 5, and a center, that's interesting, okay, at 5, 4. Sketch a phase portrait for the system around these equilibria for the node and the spiral. Remember to include arrows in your, sure, sketch a phase portrait for the system. All right, to include your arrows in your trajectory. Remember to include arrows in your trajectories to specify the directions that the solutions are moving. For the spiral, determine whether the trajectories travel clockwise or counterclockwise. So clearly I don't have, but you would need the actual system of differential equations to be able to find the direction of the spiral, for example. We don't have that, that's fine. Let's talk about drawing the picture though. So if I was going to draw this picture, so I have a saddle at -2, 5. I have an unstable node at -1, 2. I have a stable spiral at 1, 5. Well, things are really close together here. And a center at 5, 4. All right. Good times. Yeah, how are you supposed to do this without more information? So let's talk about the center over here first. So for the center, we know that we're kind of just going around in circles, for lack of a better term. I can't tell which way I'm going because I don't have the equations. I say you would need the equations, but what you could, so for example, I'm going to make something up just to kind of, let's pretend, I'm making something up here is dicey, but let's pretend that we had dx dt equal to, gosh, this is a little bit silly, but fine. Let's say x plus y and dy dt is 2x minus 3y. I'm quite well aware that these differential equations would not lead to all these equilibria, but we're just making something up so I can show you how I would kind of think about this. So let's say I'm over here in this spiral, this neutral spiral, and I want to figure out which way it goes. Well, I'm going to pick a point close to 5, 4, maybe like 5, 5. Sorry, 6, 4. So there's 6, 4. If I plug in 6, 4 to my differential equations, at 6, 4, dx dt is going to be 10. dy dt is going to be 0, which was kind of an accident, but it's fine. Means we're going purely to the right. Okay, let's look at a point below it here. Let's say we want, or maybe even, let's look over here. Let's look at the point 5, 3. If I plug in 5 for x and 3 for y, the dx dt is going to be 8. dy dt is going to be 10 minus 9 is 1. So we're going up and to the right, but way more right than up. So it kind of looks like we might be like, so the idea here is to pick a few points, and let's pick one more, like maybe say 4, 6, which is also going to be 10, and but now it's going to be negative, so it's going to be that way. right? Because dx dt is going to be 10 and dy dt is going to be negative 10. So it kind of looks to me like we're going that way. It looks like we're going counterclockwise. So that's how I would figure out the clockwiseness or counterclockwise of your spirals, is by picking points around the equilibrium where the spiral is, and then trying to just see which way things are going. That's probably the easiest way to do it. Yeah. No, you get to pick. Well, so in this problem, the way I'm imagining it is you're going to be given the differential equations, and maybe you're going to be, no, I feel like she has to tell you I mean, right. So she could give you the equilibria. She could also ask you to find them though, right? And she also asks you to find them and then classify them using the Jacobian. And then once you've done both of those things, then in the next one, be like, okay, now draw the stuff. But I could see, I could imagine that being like the problem where you also have to do the Jacobian stuff, right? Like there's already going to be a problem where you have to find the Jacobian of your, or find like the equilibria of your nonlinear system of differential equations, and then classify each of those equilibria using the Jacobian. And then she could just say, instead of giving you new stuff, use the stuff I already gave you. Maybe. Or she could give you totally new stuff. Either way, you've got your system of differential equations, and you've got the equilibria and how they're looking. So, yeah, the problem here is like for this saddle negative 2,5, I'm not really sure like which way the eigenlines are going. Like I would probably have to plug in more points over here to figure out what's going on. So to answer your question, no, you're not going to be given extra points. But to me, the easiest way to draw the phase plane here is to pick some points close to what's happening over here. So like, and again, I know this equation isn't really jiving with what I've done here because it's not the equation that this came from. But if it was, like, so over here at negative 2,5, I might pick like negative 3,6 and say, okay, well, negative 3,6, dx dt is 3. I'm going to be going right. And dy dt is, what's negative 3,6? I'm meaning negative 6 minus 18, so very negative. Like negative, I don't know, 24 maybe? Sure, negative 24. So we're going right and very down. So it looks like we're kind of going that way. So I would imagine that we're probably doing something like this, at least in the vicinity of that, saddle point right there. But again, without having the equations, it's a little bit hard to actually kind of do the work. But I think for me, well, for you really, the easiest way to kind of figure out which direction things are going is to plug in points near your equilibria to your system of differential equations and kind of see what you get. Yeah. I think for all the points. Well, I mean, that's not true. Right, because for a stable, well, I should say for the unstable node, negative 1, 2, we know things are going out away from it. So, yeah, maybe like that. Sorry, the problem, yeah, and the thing is like this gets challenging because things like there's like this area of like just wonkiness in the middle, kind of between these two equilibria. And then for our stable spiral, we know we are spiraling inwards around it, but we don't really know the direction. Right, we're kind of going like that and like that and like. But obviously, my picture is a giant mess that looks terrible right now. I don't think that's an option for nonlinear differential equations. Right, because I mean, you could take the Jacobian for that equilibrium and find the eigenvalues and the eigenvectors for it, but that's something we don't usually do. I'm really wondering what her intent with this problem is. I don't have a good, I mean, yes, you could do that. I don't think it's necessarily what should be required to do it, but I can't think of a better way to do it. So that is an option.
Should I do it tomorrow or?
I mean, I would do every other problem on the test before I did this problem is what I would do. And then depending on how much time I had, I would do what I could on this problem.
Okay.
I just, yeah, I don't. because I think this is replacing like the problem in the practice test that had like gave you a bunch of different graphs and had you identify what's going on. I don't see how you write a question like this. Because we don't usually graph the non-linear. That's not true. Definitely in previous classes. The problem is we've skipped all the stuff that we talked about how you would actually graph this kind of thing. And it is an involved process. So yeah, I don't know. I'm not sure how she expects you to really do this. Yeah. Did it feel approachable? Yeah. Well, we should probably stop because it's 1:32. But I can go look at it because I have access to her lecture notes. But yeah, I don't know. I don't feel like I have a good answer as to like how you should approach that problem on the exam because I really don't know what her expectation is for how you're going to do it. So, I mean, you certainly know what the words mean, right? A node means things are either, if it's a stable node, things are going in towards it. If it's unstable, things are going out away from it. If it's a stable spiral, things are spiraling inwards. You have to figure out which clockwiseness it is. If it's an unstable spiral, spiraling outwards. And if it's a saddle, saddles kind of do this thing where, yeah, there's some sort of eigenlines, and then we kind of go in one direction, out the other direction. Yeah. Oh, interesting. Okay.
And the problem, she gave us the system and some points in it. So that's what she drew.
Like, how would you know the saddle went that way? I don't love it. But I don't know what else I would do. So looking at her example here, I guess you should try and draw things just locally to each equilibrium and not like kind of worry about the parts where they would end up overlapping with each other. Right. Okay. So basically, okay, even though we're out of time, here's what I would say. So if I was doing this one again, here's what I would do. Let's see. So we had -2, 5. And -1, 2, and 1, 5. Again, I think all these are too close to each other, and 5, 4. Or maybe this one. So for 5, 4, it's a stable spot. Oh, sorry. Oh, I haven't put things. Oh, a set. So we have a center at 5, 4. So we're going around and around, but we're not going inwards or outwards. We're staying in a loop. That's a better word. Center is a loop. Whereas over here for our stable spiral here, we are spiraling inwards. So I would draw this as like that, where the arrows are pointing inwards towards my equilibrium. And again, I just made up that I thought that it was going clockwise. You should actually find which way it's going by trying to plot some points, not to actually plot those points, but just to determine the clockwise or counterclockwise. Over here, we have our saddle. So yeah, this is where you should just, I guess, pick a direction and be like, okay, do, and we're going like this. You should always be going outward along the same line and inward along the other same line. So this line is the one I picked to be the outward one. This line is the one I picked to be the inward one. Feels a little hand wavy there, but that's the idea. There's a saddle. And then finally over here, my unstable node, things are emanating away from it. It's not super like, it doesn't have to be like straight away from it because things do kind of arc. But that's the idea, is we're going outward from it. So that's how I guess we would draw.